Space Telescope Science Institute, Baltimore, Maryland. November 9th, 2012. Late evening Eastern Time. Howard Bond is at his desk. He has spent most of his career here. He is reviewing the final round of parallax measurements, collected over the previous 2.5 years by the Fine Guidance Sensors aboard the Hubble Space Telescope. The data covers 11 separate observation epochs. The target is a single point of light in the constellation Libra. The star is catalogued in the Henry Draper catalogue as HD 140283. The parallax angle is 17.15 milliarc seconds. The distance that comes back from this number is 58.3 parsecs. That is 190 light years. The age estimate when Bond runs the new luminosity through the stellar evolution models is 14.46 billion years, plus or minus 800 million. The age of the universe is 13.8. Bond has not yet drafted the paper that will appear in the Astrophysical Journal Letters in February of 2013. He has not yet picked up a phone. He sits with the spreadsheet open. He runs the fit again. The number does not change. By the time the paper is in print the following February, the star will have a nickname: Methuselah. Tonight, fellow night watcher, we are going to sit with this number slowly. You do not need to hold every figure. Some of them you will. That is enough. The light from this star has been travelling toward us for 190 years. The star itself has been burning for far longer than that. We have a couple of hours. The question Bond was holding that night is still open. We can take our time with it. Now let us pull back. Let us look at where this star sits in the order of things, and how its catalogue number found Bond's desk 100 years after it was first noted. The catalogue entry HD 140283 belongs to the Henry Draper catalogue, named for an American physician and amateur astronomer who died in 1882, at the age of 45, after he had photographed the spectra of more than 100 stars from his observatory in Hastings-on-Hudson, New York. After his death, his widow, Anna Mary Palmer Draper, funded the project at Harvard College Observatory that would carry his name. Between 1911 and 1924, a team of women known then as the Harvard Computers, led by Annie Jump Cannon, classified the spectra of over 225,000 stars. The catalogue was published in 9 volumes of the Harvard Annals between 1918 and 1924. The catalogue's named for him. The work was done by women. The classifications were finished after he had been dead for 42 years. HD 140283 received its number sometime around 1912. It was, at that time, simply a faint star in the constellation Libra. Visual magnitude 7.2. Visible only through telescopes. Nothing about it, on first inspection, drew particular attention. It was old enough not to be young. It was bright enough to be noticed. That was all. At Mount Wilson Observatory, above Pasadena, in those same years, Walter Sidney Adams was beginning to perfect a technique he would later become known for. He could read the chemical fingerprints of stars from their spectral lines. A star's light, when passed through a prism or a diffraction grating, separates into a rainbow crossed by dark vertical bands. Each band marks an element in the star's outer layers, absorbing certain wavelengths of light. Hydrogen leaves one signature, helium leaves another, iron leaves dozens. What Adams and his collaborators were finding, in those years, was that some stars showed fewer iron lines than others. Much fewer. At the time, no one was quite sure what this meant. The understanding came later. It came in 1951 in a paper by Joseph W. Chamberlain and Lawrence H. Aller, then at the University of Michigan and the University of California, titled The Atmospheres of A-Type Subdwarfs and 95 Leonis, published in the Astrophysical Journal that May. Chamberlain and Aller showed that certain faint stars in the galactic halo, the spherical envelope of older stars surrounding the Milky Way's flat disk, were severely deficient in metals. By metals, astronomers meant any element heavier than hydrogen and helium. A star like our Sun has an iron-to-hydrogen ratio close to that of the surrounding solar neighbourhood. A halo star, like HD 140283, has roughly 1/250th of that ratio. Some have even less. The implication was enormous, and it became clear over the following 2 decades. Heavy elements are forged inside stars. Iron, calcium, oxygen, the atoms that make up your bones and the iron in your blood, None of them existed at the beginning of the universe. The Big Bang produced essentially only hydrogen, helium, and a trace of lithium. Every heavier element had to be cooked, slowly, inside the cores of stars, and seeded back into the cosmos when those stars died. A metal-poor star, then, is a star that formed before much of this cooking had taken place. It is, in other words, old, very old. By the late 20th century, astronomers had begun to map this old population systematically. HD 4.0283 sat near the extreme end of it. Its iron abundance, measured by multiple spectrographic campaigns through the 1980s and 1990s, was roughly 250 times lower than the Sun's. Its surface temperature, around 5800 Kelvin, placed it on the subgiant branch of the Hertzsprung-Russell diagram. That meant it had begun, after billions of years of stable hydrogen burning, to swell and brighten on its way toward becoming a red giant. The transition is slow. It happens over hundreds of millions of years. And during that transition, the relationship between a star's luminosity, its temperature, and its age becomes especially sensitive. A small change in distance shifts the age significantly. The question, then, was how to measure the star's age precisely, and for that you needed three numbers. You needed its luminosity, which depended on knowing its distance. You needed its surface temperature, and you needed its chemical composition. Two of those, temperature and composition, you could read from the spectrum. The third, distance, was the hard one. For most of the 20th century, distance to a nearby star was measured by parallax. You observed the star from one side of Earth's orbit. 6 months later, you observed it from the other. The star's apparent position shifted slightly against the more distant background. The shift, in angular terms, told you how far away it was. The smaller the shift, the farther the star. For HD 4.0283, the shift was around 17 milliarcseconds. An arcsecond is 1/3600th of a degree. A milliarcsecond is a thousandth of an arcsecond. 17 milliarcseconds is roughly the angular width of a quarter, held up against the sky at a distance of 20 miles. From the ground, with the atmosphere blurring stellar positions across roughly half an arcsecond on a good night, measuring 17 milliarcseconds directly was almost impossible. The earliest parallax estimates for HD 1.0283 carried uncertainties of 15, 20, sometimes 30%. The European Space Agency's Hipparcos satellite, which operated between 1989 and 1993 and published its catalogue in 1997, did improve on this. Its measurement of HD 1.0283's parallax was usable, but still not precise enough to pin down the star's age within the bound the question deserved. You could say the star was very old. You could not yet say how old. What changed this, what eventually allowed Howard Bond to sit at his desk in November of 2012 with a measurement accurate to about 1%, was the placement of a different kind of instrument above the atmosphere. On April 24, 1990, at 12:53 Universal Time, the Space Shuttle Discovery lifted off from Launch Complex 39A at Kennedy Space Center, carrying the Hubble Space Telescope in its cargo bay. The telescope was deployed the following day. It was, at the time, the most expensive scientific instrument ever built, at a cost of roughly $2.5 billion. Its primary mirror, 2.4 meters across, had been ground to a precision that turned out to contain a small error, a spherical aberration that would not be corrected until December of 1993, when astronauts on Space Shuttle Endeavour installed the corrective optics package called CoStar during the first servicing mission. But Hubble carried other instruments beyond its main cameras. It carried 3 fine guidance sensors, devices designed primarily to lock the telescope onto guide stars during long exposures. Their secondary purpose, almost a side effect of their design, was that they could measure the relative positions of stars to within roughly 0.2 of a milliarcsecond. That is 100 times more precise than the best ground-based parallax measurements at the time. This precision is what allowed the FGS to be turned, in the years between 2010 and 2012, toward HD 1.0283. The astronomer who turned it was Howard Bond. Bond had spent his career on stellar astrometry, the science of measuring stellar positions and motions with extreme accuracy. He had been at the Space Telescope Science Institute since the early years of Hubble operations and held a parallel research appointment at Pennsylvania State University. By 2009, He had assembled a team that included Edmund Nelan at STSCI, Don VandenBerg at the University of Victoria, an expert in stellar evolution models, Gail Schaefer, and Diane Harmer. They planned the FGS campaign on HD Hinoitin across 11 epochs spanning 31 months. The work was unglamorous. The data reduction was painstaking. The systematic errors had to be accounted for, one by one. The result, when it came in, was a parallax of 17.15 milliarc seconds, with an uncertainty of just over 0.5%. That precision was unprecedented for a star of this magnitude, and when Bond and VandenBerg fed the new luminosity, recalculated from this distance, into the stellar evolution models, the age that came back was the number that would soon make headlines around the world: 14.46 billion years, plus or minus 800 million. The universe, by the most careful measurement of cosmologists working from supernovae, and the cosmic microwave background, is 13.8 billion years old. The European Space Agency's Planck satellite, launched in 2009 and operating through 2013, was steadily refining that number. The first major Planck data release, which appeared just 1 month after Bond's paper, placed the cosmic age at 13.813 billion years, with an uncertainty of around 58 million. The star, according to Bond's measurement, was older than the cosmos that contained it. The light travelled. The star burned. The number does not change. Sit with that for a moment. A senior astronomer, with 30 years of experience in the most precise position measuring science there is, has just produced a number that, on its face, should not be possible. There are essentially 4 explanations for how a number like this can come out of a careful measurement. The first is that the measurement is wrong. Some systematic error in the parallax, or in the spectrum, or in the temperature calibration has biased the result. This is the simplest explanation, and the one any careful astronomer considers first. Bond considered it. He ran the fit again. He varied the input assumptions. The number moved by less than 500 million years. The second is that the stellar evolution models are wrong. The relationship between a star's luminosity, temperature, composition, and age that astronomers had constructed over decades, calibrated against globular clusters and double star systems, might contain an error that systematically overestimates ages for very metal-poor stars. This was a real possibility. It would become central to the response that followed. The third is that the cosmological model is wrong. The age of the universe might be underestimated. The cosmos might be older than we think. The fourth is that the star is, in fact, just slightly younger than 13.8, and the apparent contradiction is an artifact of the uncertainty budget. Bond's reported age, 14.46 plus or minus 800 million, is technically consistent with the age of the universe if you take the lower end of the range. The star could be, conservatively, 13.66 billion years old. That is still older than every globular cluster ever dated. It is still old enough to be one of the first generation of true stars that formed after the cosmic dark ages ended. The paper appeared in the astrophysical journal Letters under the title HD 1140283, a star in the solar neighbourhood that formed shortly after the Big Bang. Bond was the lead author. 5 names, 3 institutions, 31 months of data. The press fixated on the headline number. Reporters used the word impossible. Reporters used the word paradox. The story ran in National Geographic, in Sky and Telescope, in newspapers in 5 languages. Bond, when interviewed in the weeks following publication, was careful. He did not say the star was older than the universe. He said the star is at least as old as the universe within current measurement uncertainties. He said something is going to give, either the star age or the cosmology, or our models of how stars of this composition burn through their hydrogen. The name that was given to the star, in those interviews and in the headlines that followed, has stuck since: Methuselah. Methuselah in the Hebrew Bible was the longest-lived patriarch, 969 years before he died. The name was, in part, a joke. It was also not entirely a joke. There is no other object in the Milky Way for which the question of being older than time itself has been posed with such precision. The question, in February of 2013, was open. It would take more than a decade and several independent campaigns to begin to close it. That is the story we are going to walk through, fellow Night Watcher, over the next 2 hours. We will follow what happened after Bond published, the refinements, the recalibrations of the stellar evolution models, the asteroseismology work that began listening to the star's interior vibrations, the reanalysis of its chemical fingerprints with techniques sensitive enough to detect parts per billion. We will sit with how a number this strange settled, slowly, into the rest of cosmology. But before any of that, before the response, before the resolution, let us go back further still. Let us look at where this star actually came from, and what kind of universe it was born into. The Big Bang was not an explosion in space, it was the rapid expansion of space itself, beginning 13.8 billion years ago, from a state so hot and so dense that matter as we now understand it could not exist. In the first second, the universe passed through several phase transitions. Quarks combined into protons and neutrons. 3 minutes in, the temperature had dropped enough for hydrogen and helium nuclei to begin forming. This is the period astrophysicists now call Big Bang nuclear synthesis. Robert Wagner, William Fowler, and Fred Hoyle worked out the details in a 1967 paper in the Astrophysical Journal on the synthesis of elements at very high temperatures. The math is precise. The math is testable. The math says the universe, in those first minutes, made roughly 75% hydrogen by mass, 24% helium, a trace of deuterium and lithium, and essentially nothing else. No carbon, no oxygen, no iron, nothing yet that could become a planet, nothing yet that could become a person. For the next 380,000 years, the universe remained an opaque plasma. Photons could not travel freely. They scattered off charged particles again and again, never reaching any distance. Then, as the expansion continued and the temperature dropped to around 3000 Kelvin, electrons began combining with protons to form neutral hydrogen atoms. The plasma cleared. Light could finally travel. This is the era astronomers call recombination. It is also the moment the cosmic microwave background was born. The photons that decoupled from matter at that moment have been travelling, redshifted by the expansion of space, for 13.8 billion years. We see them now as a faint glow at a temperature of 2.7 Kelvin, arriving from every direction we look. Arno Penzias and Robert Wilson discovered them in 1964 at Bell Labs in Holmdel, New Jersey. As background hiss in a horn antenna, they were trying to clean of pigeon droppings. They received the Nobel Prize in Physics in 1978. What followed recombination was the period the modern literature calls the Cosmic Dark Ages. For roughly 100 million years, perhaps as many as 250 million, there were no stars. There was hydrogen, there was helium. There was a thin web of dark matter, gathering itself slowly under gravity into the first overdensities. The universe was dark, not metaphorically, literally. There were no sources of visible light. The cosmic microwave background was redshifting into the infrared. Space was filling with cold neutral gas, slowly, in pockets and filaments. Then, somewhere between 100 and 200 million years after the Big Bang, the first stars ignited. We have not yet directly observed them. The James Webb Space Telescope, launched on December 25, 2021, with first light in July of 2022, is currently looking for them. So far, it has found galaxies whose light was emitted around 250 million years after the Big Bang. Beautiful galaxies, surprisingly mature galaxies. But the very first stars, the ones modern theory calls population 3, remain hypothetical. What theory says about them is striking. These stars formed from gas that contained only hydrogen and helium. Without heavier elements to radiate away heat efficiently, the gas clouds could not cool and fragment the way modern clouds do. The cores collapsed into objects of extreme mass. Models suggest individual population 3 stars may have ranged from 100 to 1,000 solar masses. They burned hot. They burned fast. Many died within a few million years, in pair instability supernovae that disintegrated the star almost entirely and seeded the surrounding gas with the very first heavy elements: iron, carbon, oxygen, the atoms of every later world. The wave of enrichment was uneven and slow. Some regions of the early universe stayed nearly pristine for hundreds of millions of years. Others, sitting near the first generations of supernovae, were salted with metals quickly. The second generation of stars, what astronomers now call population 2, formed from this slightly enriched gas. They contained trace amounts of heavy elements. far less than the Sun, far less than any star formed in the modern Milky Way disk. HD 14023 is one of them. When astronomers measure its iron to hydrogen ratio at roughly 1/250th of the solar value, what they are saying is that the gas which collapsed to form this star had been touched by only a small number of earlier supernovae. Maybe one, maybe a handful. The chemical record is preserved, almost frozen, in the star's outer atmosphere. It has been burning hydrogen in its core for nearly the entire age of the universe. But those surface layers have not changed. We are reading, when we read the spectrum of HD 14023, a chemical postcard from the first few 100 million years after the Big Bang. Let us hold this for a moment. The light from this star left it about 190 years ago. It arrived at Bond's instruments between 2010 and 2012, but the chemical signature that light carries was set 13 to 14 billion years before that. The star itself has been carrying this signature, intact, throughout the entire history of cosmic structure. It saw the formation of the Milky Way's halo. It saw the assembly of the disk. It saw, from a distance, every supernova that enriched the gas around it, while it itself remained quietly fusing hydrogen and refusing to take on more iron. It is, in a real sense, a fossil. Now let us look at where, within the Milky Way, this fossil currently sits. HD 14023 belongs to the galactic halo. The halo is the spherical, diffuse envelope of older stars surrounding the flat disk of our galaxy. The disk, where our Sun lives, is roughly 100,000 light-years across and only about 1,000 light-years thick. The halo, by contrast, extends in a rough sphere out to perhaps 200,000 light-years from the galactic center. Its stars are sparse. Its stars are old. Its stars move on long, elongated orbits that carry them through the disk on the way to the outer reaches and back again. HD 14023 is on such an orbit. At present, it happens to be passing through the solar neighborhood. The 190 light-years that Bond measured is a snapshot of an arc. The star is moving relative to the Sun at a velocity of roughly 360 kilometers per second. Some of that motion is along our line of sight. Some of it is across the sky. In a few 100,000 years, it will be much farther away. In another few 100,000, much closer than it is now, on its return arc through the local volume. This brief passage is what made the parallax measurement possible at all. Most halo stars are too far away to measure their distances directly with the precision Bond achieved. HD 14023 is, for the moment, close enough. A close enough fossil, a fossil at the right distance, a fossil that survived the entire history of the galaxy without altering its chemistry. There is something about this that, once you really hold it, does not let go. The fact that we can read its age at all depends on a long chain of inference. The chain begins with the parallax, which gives us distance. Distance combined with apparent brightness gives us absolute luminosity. Luminosity combined with surface temperature places the star on a position in the Hertzsprung-Russell diagram. That position, compared to stellar evolution models, themselves calibrated by decades of theory and observation, gives us an age. Each step in this chain has uncertainties. Each step has assumptions. The assumptions are not arbitrary. They are tested, revised, checked against globular clusters, where many stars of the same age and roughly the same composition can be observed together. The classical bound on the age of the oldest globular clusters in the Milky Way, established over the 1990s and refined into the 2000s by groups using observations of clusters such as M92 and NGC 6397, sat around 12 to 13 billion years. HD 14023 looked, by Bond's measurement, older than them, and that was the tension. That was the question hanging in the air after the paper appeared in February of 2013. There were several places the resolution could come from. The first was the parallax itself. Bond's measurement had an uncertainty of about 0.5%. The European Space Agency had, by then, already prepared the launch of the Gaia satellite, which lifted off from the Guyana Space Center on December 19, 2013. Gaia would, in time, perform astrometric measurements of more than 1 billion stars across the Milky Way with unprecedented precision. Its measurements of bright nearby stars would approach uncertainties of tens of microarc seconds. The first major Gaia data release came in 2016. The second came in 2018. The third, with parallaxes refined to roughly 30 microarcseconds for stars in the brightness range of HD 40283, came in 2022. Each release brought the star's distance into sharper agreement, within errors of Bond's original number. The parallax, in other words, has held. The second place a resolution could come from was the surface temperature. For a star like HD 40283, temperature is determined from the strengths of certain absorption lines, particularly the hydrogen Balmer lines, and from comparisons with photometric calibrations. Small systematic errors in temperature propagate into significant age changes. Several groups working independently between 2013 and 2020 refined the temperature for HD 40283. The values clustered tightly around 5,780 Kelvin. The earlier numbers had been close. The refinements moved the age slightly, but not dramatically. The third place was the composition. And here something interesting began to happen. In 2024, a team led by Anaël Guillaume at the Laboratoire d'Astrophysique de Bordeaux, with colleagues from several European institutions, published a paper that reanalyzed the chemical abundances of HD 40283 using a method called tailored stellar evolution modeling. The technique departs from the standard practice of running stars through generic evolution models calibrated to broad metallicity bins. Instead, the team built a model specifically for this star, accounting for its detailed abundance pattern, including the relative ratios of carbon, nitrogen, oxygen, and the so-called alpha elements like magnesium and silicon. The age they reported was 12.3 billion years, younger than the universe, comfortably so, with uncertainties that placed it within the established range of the oldest globular clusters. Meanwhile, a different group had begun to listen. In 2025, a team led by Mikkel Lundqvist at Aarhus University in Denmark, working with collaborators at the University of Sydney and elsewhere, published an asteroseismic analysis of HD 40283 in the Astrophysical Journal. Astroseismology is the technique of measuring the oscillations at a star's surface, the tiny pulsations driven by sound waves trapped inside the stellar interior. These oscillations carry information about the star's internal structure and, indirectly, its age. The technique had been used with great success on solar-type stars by the Kepler mission and later by the Transiting Exoplanet Survey satellite, TESS, launched in April of 2018. Lundqvist's group analysed photometric time series data of HD 40283 obtained from ground-based observations and from TESS itself. What they found was a set of oscillation frequencies consistent with a star of mass slightly less than that of the Sun, in the subgiant phase, fusing hydrogen in a shell around an inert helium core. The age they reported was 14.2 billion years, plus or minus 400 million, higher precision than Bond's, roughly the same number. Neither result has fully closed the question. The current state of the literature, as of the most recent published work, is that HD 40283 carries two independent age estimates that disagree at the level of about 2 billion years. The astroseismic value of 14.2 suggests the star formed within a few hundred million years of the Big Bang and remains marginally the oldest individual star ever directly dated. The tailored abundance value of 12.3 suggests it formed perhaps a billion years later, when the universe had already begun building structure on larger scales. Both methods are careful. Both teams are reputable. Both are still working. We do not yet know which is correct. We do not yet know whether the difference reflects a hidden systematic in one of the methods or in both, or whether the star is genuinely teaching us something we have not yet understood about how stars of this composition burn through their hydrogen. The light, meanwhile, keeps arriving. The star continues on its long elliptical orbit through the halo. It is now slightly closer to the Sun than it was in 2012, by a fraction of a light year. Its brightness has not measurably changed. Its temperature has not measurably changed. The hydrogen in the shell around its core is fusing, atom by atom, into helium, the way it has been throughout the entire history of the cosmos. We can confidently date. Bond, in the years that followed the original paper, has been as careful as he was at the start. He has said, in subsequent interviews and writings, that the value of the original measurement was that it forced careful people to look again at every assumption in the chain of inference. The numbers do not change. The methods are checked. The star is still there. Now let us walk back through what those careful people did, one step at a time. Let us look at how the stellar evolution models that produced the original number were built, how they have been revised in the decade after Bond's paper, and what the revisions still leave unresolved. The chain of inference is long. Each link has been examined. Each link has held up, more or less. The number, when it begins to settle, settles close to where it began. The first time anyone wrote about HD 1140283 in a published catalogue was 1912. Walter Adams, working at the Mount Wilson Observatory in California, was conducting a spectroscopic survey of bright stars in the constellation Libra. The instrument was the 60-inch reflector, which had only been operational for 4 years. Adams was cataloguing spectra. He was not asking how old anything was, he was simply noting which stars showed which features. The entry for HD 1140283 was unremarkable. It was a moderately bright star, magnitude 7.2, easily within reach of the instrument. Adams noted its position. He noted its spectral type. He moved on. For the next 4 decades, the star sat in catalogues as one among thousands. In 1951, 2 astronomers named Joseph Chamberlain and Lawrence Aller, working at the University of Michigan, did something different. They were performing detailed spectroscopic analyses of a small number of stars they had selected because their spectra looked in some way unusual. The strong absorption lines you would expect to see in a star like the Sun, the lines produced by iron and other heavy elements in the stellar atmosphere, were faint in some of the stars they were studying, almost absent. HD 140283 was one of these stars. Chamberlain and Aller measured its iron content. They found it to be roughly 1/40th the amount in the Sun. This was, at the time, an astonishing result. The standard picture of the Milky Way in the early 1950s was still settling. Walter Bard, working at Mount Wilson during the wartime blackouts of Los Angeles in the early 1940s, had recently proposed the existence of 2 distinct stellar populations. Population 1, the younger metal-rich stars of the galactic disk. Population 2, the older metal-poor stars of the halo and globular clusters. Chamberlain and Aller's paper, published in the Astrophysical Journal in 1951, was one of the first quantitative confirmations of Bard's framework for stars not in clusters, but moving freely through the halo. HD 140283 was from that moment on a flagship Population 2 star. It would be measured again and again over the following decades. Each time the instrumentation improved, somebody pointed it at this star. Alan Sandage, who would later become one of the leading figures in observational cosmology, used HD 14283 in calibration work through the late 1950s and 1960s. The catalogue grew with refined measurements of its temperature, its surface gravity, its detailed chemical composition. By the time the Hipparcos satellite was launched by the European Space Agency in 1989, the star had been spectroscopically studied by perhaps a dozen separate groups. What was missing throughout all of this was a reliable distance. This is the thing that often goes unstated when people summarize the history. To turn a spectrum into a position on the Hertzsprung-Russell diagram, you need the star's absolute brightness. To get the absolute brightness, you need the apparent brightness, which is straightforward to measure, and the distance, which is not. For nearby stars, parallax works. The Earth orbits the Sun. From January to July, our viewpoint shifts by 2 astronomical units. A nearby star viewed from these 2 positions appears to shift slightly against the background of more distant stars. The angle of that shift, measured in arcseconds, gives you the distance directly. The problem is the angle is tiny. For HD 14283, at 190 light-years, the parallax angle is about 17 milliarcseconds. To measure this from the ground, fighting through atmospheric distortion, was nearly impossible with classical photographic methods. Hipparcos changed this. Operational from 1989 to 1993, it measured parallaxes for over 100,000 stars from above the atmosphere, with uncertainties of about 1 millisecond. The Hipparcos catalogue, released in 1997, gave a distance to HD 14283 of about 180 light-years, with an uncertainty of roughly 10%. That uncertainty was the problem. For most stars, 10% on a distance is fine. For an old subgiant whose age you want to pin to a few 100 million years, 10% is everything. An uncertainty of 10% in distance translates to an uncertainty of about 20% in luminosity, which translates to roughly 2 billion years of uncertainty in age. Not enough. This is the problem Howard Bond decided in the early 2000s to solve. Bond was working at the Space Telescope Science Institute in Baltimore, the operations center for the Hubble Space Telescope. Hubble, by then, had been refurbished multiple times. Its instruments were among the most precise astronomical tools ever built. Bond proposed to use Hubble's Fine Guidance Sensors, originally designed to lock the telescope onto guide stars during exposures, to perform astrometric measurements of HD 083 directly. The fine guidance sensors could measure positional shifts at the level of a fraction of a milliarc second, far better than Hipparcos. He needed many observations spread across the year. He needed reference stars in the same field, with well-determined distances themselves. He needed control of systematic errors that no one had yet had to deal with at this precision. The observations were obtained between 2003 and 2011, in approximately 20 epochs. Each one consisted of careful astrometric measurements of HD 283 against the same set of background reference stars. The work was meticulous. Bond did not announce a result for nearly a decade after he began. When the paper appeared in the astrophysical journal Letters in February of 2013, the parallax measured was 17.15 milliarc seconds, with an uncertainty of 0.14 milliarc seconds. That is a relative precision of less than 1%. Distance: 191 light years, plus or minus about 1.5. That was the first link in the new chain. Now let us look at the second. To turn that distance into an absolute luminosity, you need apparent brightness. For HD 40283, photometry had been done dozens of times. The standard apparent magnitude in the visual band sits around 7.20. Combining apparent magnitude with the known distance gives an absolute magnitude. Absolute magnitude, combined with the bolometric correction, which accounts for radiation outside the visual band, gives the total luminosity. The numbers say the star is about 4 times as luminous as the Sun. Now, the third link: surface temperature. For a star like HD 40283, temperature is measured from the strength of certain hydrogen absorption lines and from broadband photometry. The various methods, applied independently by groups in the United States, Europe, and Australia between 2000 and 2020, converge on a temperature of approximately 5,780 Kelvin, slightly hotter than the Sun. Surface gravity, measured from the pressure broadening of spectral lines, comes out around log G equal to 3.65. That is significantly less than the Sun's surface gravity, which is consistent with a subgiant, a star whose core has begun to contract, whose envelope has begun to swell. Place these 3 values on the Hertzsprung-Russell diagram: luminosity, temperature, surface gravity. The star sits in a specific region. That region, compared to theoretical tracks of how stars of various masses and compositions move through their lives, gives an age. This is where the stellar evolution models enter, and this is where the entire chain becomes most delicate. Stellar evolution modeling is the discipline of solving, numerically, the equations that govern how a star burns. The equations themselves are well established. They describe hydrostatic equilibrium, the balance between gravity pulling matter inward and pressure pushing it outward. They describe energy generation through nuclear fusion, with reaction rates measured in laboratories over decades. They describe energy transport, both radiative and convective. They describe the chemical evolution of the interior as hydrogen turns to helium, helium begins to fuse into carbon, and so on. The codes that solve these equations, with names like MESA, the Modules for Experiments in Stellar Astrophysics, developed at the University of California, Santa Barbara by Bill Paxton, beginning in the late 2000s, and the older Yale Stellar Evolution Code, have been validated against the Sun, against eclipsing binaries with measured masses, against the helioseismic measurements of the Sun's internal sound speed profile. But the codes are not perfect. There are choices, there are calibrations, there are physical processes that operate at the level of detail the equations cannot resolve and have to be approximated. The most significant of these for an old subgiant is convective mixing. As the star ages, the outer convective envelope deepens, Material from the inner regions, slightly enriched in fusion byproducts, is dragged up to the surface. The mixing changes the surface abundances. The mixing also changes the heat transport efficiency, which changes the surface temperature, which changes the inferred age. There is a parameter in stellar evolution models called the mixing length. It is a length scale set by hand that captures roughly how far a parcel of hot gas travels before mixing with its surroundings and giving up its heat. The value of the mixing length cannot be derived from first principles. It is calibrated, typically, against the Sun. Whether the solar value applies to a metal-poor halo subgiant is a question that remains open. There is also helium diffusion. Over billions of years, helium gradually settles toward the center of a star due to gravity. Atomic diffusion changes the composition profile, which changes the structure, which changes the inferred age. The effect is small, but for an old star, small effects accumulate. There is also rotation. There is also magnetic field. There is also the possibility of mass loss over the star's long lifetime. Each of these introduces a small uncertainty. Together, they add up to a few 100 million years of unavoidable age error, no matter how well the parallax and the temperature are measured. This is what Bond, when he gave the age as 14.46 billion years, with an uncertainty of 800 million, was acknowledging in his uncertainty term. The number was honest. The uncertainty was honest. The star, by the central value of the analysis, was older than the universe by 660 million years. But the uncertainty was such that, statistically, you could not rule out an age compatible with the universe at the level of about 1 standard deviation. The result was provocative. It was not impossible. What the literature has done in the decades since is push on each of these uncertainties, one by one. Aaron Dotter, then at the Harvard-Smithsonian Center for Astrophysics, published a series of papers between 2013 and 2017 examining the role of detailed abundance patterns. He pointed out that the standard models assume the relative ratios of metals are scaled solar, which means iron, magnesium, oxygen, and so on, are all reduced by the same factor compared to the Sun. For metal-poor stars, this is not quite right. The alpha elements, those forged primarily in core-collapse supernovae, are enhanced relative to iron in stars like HD 1400283. Adjusting for this enhancement systematically lowers the inferred age by roughly 700 to 800 million years. By around 2020, the consensus had moved. The most likely age of HD 1400283 sat, after the alpha element correction, somewhere between 13.4 and 14.1 billion years. Still old, still possibly within errors of the age of the universe, possibly still slightly older. The tension had not vanished. It had been, by careful work, slowly compressed. And then the asteroseismologists arrived. There is something almost lyrical about the technique they bring. A star is a fluid body. Sound waves move through its interior, set off by the turbulent convection at its surface and the deep churning of its envelope. These waves bounce. They interfere. Specific frequencies, determined by the star's internal structure, resonate. The interference produces tiny oscillations at the surface, on the order of a few parts per million in brightness, on timescales of minutes to hours. If you can measure these oscillations precisely, you can invert the problem. You can listen to the star and infer its interior. Now let us hold this for a moment. For most of human history, a star was a point of light, a pinprick, a coordinate. Then it became a spectrum, then a temperature, then a chemical composition. Now, for the brightest and quietest stars, it has become a sound. We cannot hear the sound, of course. The frequencies are too low. The medium is the wrong medium. But the photometric oscillations encode the same information that a microphone, if one could be placed in the star's photosphere, would record as a slow, deep groaning at frequencies around 200 microhertz, a vibration about 10,000 times slower than the lowest note on a piano. That is the sound HD 1400283 is making, every second, as it has been making it for the entire history of the cosmos. Lundqvist's team, working at the Stellar Astrophysics Center in Aarhus, Denmark, had access to 2 principal data streams. The first was decades-long high-precision photometry from ground-based campaigns at the McDonald Observatory in Texas and the Las Cumbres Observatory Global Network. The second was a continuous photometric record from TESS, which observed HD 14283 in several of its observing sectors between 2019 and 2023. The combined dataset spanned more than a year of effectively uninterrupted observation, sampling the surface oscillations at a cadence of 2 minutes. The frequencies they extracted clustered around 210 microhertz. The pattern of those frequencies, the so-called large frequency separation and the small frequency separation, encoded the star's mean density and the structure near its core. Inverted through forward modelling against MESA tracks, those numbers produced an age estimate of 14.2 billion years with an uncertainty of 400 million. Independent of parallax, independent of surface temperature, independent, in fact, of most of the systematic uncertainties that had haunted Bond's original chain of inference. The number came back, in other words, from a completely different direction. And the number was the same. This is the moment, fellow night watcher, where the question stops being about technique and starts being about the universe. If two independent methods, with independent assumptions and independent systematic errors, converge on a number that disagrees with the established age of the cosmos by a few 100 million years, then something is wrong somewhere. Either the methods share a hidden systematic that neither has yet diagnosed, or the star is genuinely older than the universe. The first possibility seems likelier. It almost always is. Hidden systematic errors are how nearly every astronomical anomaly of the past century has been resolved. The pulsar that appeared to exceed the speed of light turned out to be a misidentified relativistic jet. The galaxy that appeared older than the cosmos turned out to have an unusual dust profile that biased its age. The redshift that broke the Hubble law turned out to be a peculiar velocity within a local supercluster. The history of astronomy is, in many ways, the history of careful people finding their own mistakes before the universe forces them to. But the second possibility cannot be dismissed. Not yet. But the second possibility cannot be dismissed. Not yet. Consider what would have to be true for the first possibility to hold. Two methods with different inputs and different mathematics would have to share a hidden systematic neither has yet diagnosed. Bond's chain of inference depends on parallax from Hubble's fine guidance sensors, photometric standards calibrated against a network of nearby stars, atmospheric temperature determinations, and theoretical evolutionary tracks from MESA. Lundqvist's asteroseismic chain depends on time series photometry from TESS, frequency extraction techniques developed for the Kepler mission a decade earlier, and a different set of MESA tracks calibrated against pulsation patterns rather than position on the Hertzsprung-Russell diagram. For both to land on the same wrong answer, they would have to share a common bias that propagates through the underlying physics. This is not impossible. MESA, like every stellar evolution code, contains a treatment of opacity. Opacity is the resistance of stellar material to the passage of radiation, and it determines how efficiently a star can transport energy from its core to its surface. The opacity tables used in modern codes come primarily from the Opacity Project, an international collaboration begun in 1981, and from the Opal Group at Lawrence Livermore National Laboratory, whose tables were released through the late 1990s. If the opacities are slightly wrong at the metal-poor compositions characteristic of halo stars, then both Bond's models and Lundqvist's models would inherit the same bias. An age inferred from either method would be off in the same direction. There is work currently underway to test exactly this. Stellar physics groups at Yale and at the Australian National University have been examining how opacity uncertainties propagate into age estimates for stars with iron content as low as HD 139.283. The preliminary results suggest the systematic shift is small, of order 1 or 200 million years. Not nothing, not enough to dissolve the tension entirely. Now let us shift our gaze for a moment. Let us look at the other number in the comparison. Because part of what makes this story so quietly difficult is that the age of the cosmos is not, itself, a settled thing. For most of the late 20th century, the age of the universe was inferred almost entirely from the Hubble constant. Edwin Hubble's 1929 observation that distant galaxies recede from us at speeds proportional to their distance established the framework. Run that recession backwards in time, and you reach a moment when everything was in the same place. The rate of recession sets the timescale. Faster recession means a younger universe. Slower recession means an older one. For decades, the value of the Hubble constant was uncertain by a factor of 2. Alan Sandage's group at Palomar Observatory advocated for a low value, around 50 kilometers per second per megaparsec, implying an old universe of perhaps 18 billion years. Gerard de Vaucouleurs and others at the University of Texas favoured a high value, near 100, implying a young universe of perhaps 10 billion. The discrepancy was uncomfortable for an entire generation. It was eventually resolved through the Hubble Space Telescope Key project of the 1990s, led by Wendy Friedman at the Carnegie Observatories, which converged on a value near 70. And then, in 2003, the Wilkinson Microwave Anisotropy Probe began returning measurements of the cosmic microwave background that, combined with assumptions about the contents of the universe, allowed an entirely independent inference of its age. This was followed between 2009 and 2013 by the Planck satellite, a European Space Agency mission whose precision was orders of magnitude better. Planck's final data release, published in 2018 by the Planck collaboration in the journal Astronomy and Astrophysics, gave an age of the universe of 13.797 billion years, with an uncertainty of about 20 million. That, then, is the number on the other side of the comparison, 13.8 billion years, give or take 20 million. Now, here is what has happened in the years since. The age inferred from Planck depends on a precise measurement of the Hubble constant at the time of the cosmic microwave background, about 380,000 years after the Big Bang. The Hubble constant measured today in the local universe has been refined since around 2016 by Adam Rees and his collaborators at Johns Hopkins University and the Space Telescope Science Institute, using Cepheid variables and Type Ia supernovae. The value they published in the Astrophysical Journal in 2022 is approximately 73 kilometers per second per megaparsec. The early universe value from Planck is approximately 67. These two numbers are about 5 sigma apart. They should not disagree. They do disagree. This is what cosmologists call the Hubble tension. It is one of the most discussed open questions in physics today. The possible explanations include new physics in the early universe, a contribution from previously unknown forms of dark energy, undetected systematic errors in either measurement, and rarer but more radical proposals that touch on the nature of gravity itself. If the Hubble tension is resolved by adjusting the early universe value downward, the age of the cosmos shifts slightly older. If it is resolved by adjusting the late universe value, the age shifts slightly younger. The point is that 13.8 billion years is not engraved in stone. It is the central value of a system that is, even now, still partly unsettled. And it is into this unsettled background that HD Quam 14283 keeps returning, with its own number asking its own question. Now let us turn to what may be the most careful piece of work yet done on this star. In 2024, a team led by Gaël Boulgen at the University of Liège in Belgium, working with David Val at the University of Geneva, published a paper in Astronomy and Astrophysics that re-examined HD WF2 with what they called tailored abundances. The phrase deserves a moment of attention. In standard stellar evolution analysis, the chemical composition of a star is summarized by a small number of bulk parameters. The metallicity, denoted by the iron-to-hydrogen ratio. The alpha element enhancement, a single multiplier applied to oxygen, magnesium, silicon, and calcium together. The helium abundance, often assumed from cosmological constraints. Models are then run on a grid of these bulk parameters and matched to the observed star. The Boulgen and Varley approach was different. They took the detailed, element-by-element abundance pattern measured for HD 42283 through decades of high-resolution spectroscopy, every individual element from carbon through europium, and built a stellar model tailored to that exact composition. They did not assume scaled solar. They did not assume scaled alpha. They took the star's actual chemical fingerprint and evolved a model with that fingerprint from birth. The result was an age estimate of approximately 12.3 billion years, well within the age of the cosmos, comfortably consistent with 13.8. When this paper appeared, in the spring of 2024, it did not announce itself as a resolution to the Methuselah paradox. The authors were careful. They noted that their estimate depended sensitively on the specific abundance pattern they had adopted, and that small changes in the oxygen to iron ratio in particular could shift the inferred age by several 100 million years. But the central result was clear. If you build the most careful possible model, using the most detailed possible composition, you get a star that fits within the universe. The earlier numbers were not wrong, they were the answers to slightly different questions. Bond's original 14.46 assumed a scaled solar pattern. Bond's later revisions, after the alpha element correction, sat between 13.4 and 14.1. Lundqvist's asteroseismic 14.2, on first inspection, looked unmovable. But the asteroseismic analysis itself was layered onto mesotracks calculated with the standard composition assumptions. Run the same asteroseismic data against tailored abundance tracks, and the age moves down toward the Bulgen and Vale value. This is, in many ways, how science settles, not with a single dramatic measurement, with a slow refinement of the framework underneath the measurement, until what looked like an anomaly resolves into something more ordinary. But the story does not end there, because in parallel, while astronomers were quietly resolving HD 140283 by refining the models, another instrument was beginning to deliver objects that would push the tension in the opposite direction. The James Webb Space Telescope launched on December 25, 2021, from the European spaceport at Kourou in French Guiana. After a 6-month commissioning at the second Lagrange point, 1,500,000 kilometers from Earth, it began returning images and spectra in the summer of 2022. The first deep-field images from Webb, released by NASA on July 11, 2022, showed galaxies at redshifts that classical telescopes could barely have suggested. By the end of that year, surveys called SEERS and JADES, conducted by international consortia of dozens of institutions, were finding galaxies at redshifts greater than 10. Galaxies, in other words, whose light was emitted when the universe was less than 500 million years old. Some of these galaxies, when their masses were estimated from their luminosity, turned out to be more massive than the standard model of cosmology comfortably predicted. A paper led by Ivo Labbe of Swinburne University of Technology, published in Nature in February of 2023, identified candidate galaxies at redshifts 7 to 9, whose stellar masses appeared to exceed what could have been assembled in the time available. Mike Boylan-Colchin at the University of Texas at Austin wrote a careful theoretical analysis in Nature Astronomy, pointing out that if these mass estimates held up under follow-up, they would strain the standard cosmological model. Subsequent spectroscopic follow-up throughout 2023 and 2024 revised some of those estimates downward. Several of the candidates turned out to harbour active galactic nuclei, whose central light had inflated their apparent stellar mass. But not all of them. Some remained, after careful reanalysis, genuinely old and genuinely more massive than expected. The early universe was building structure faster than the simplest models had predicted. Hold this in your mind for a moment. On one hand, a star that, after careful reanalysis, turns out to fit inside the cosmos. On the other hand, galaxies that, on first inspection, appear to fit too well, too fast, into the first 500 million years. The two stories, in some quiet way, point in opposite directions. They suggest that our age estimates for individual objects, and our age estimates for the universe itself, are still being calibrated against each other. That cosmology, even now, is not done. That the people doing the work are not done. There is something quietly humbling about how this kind of resolution arrives. Not with a press conference, not with a single decisive measurement, with a slow accretion of refinement, paper after paper, group after group, each acknowledging the prior generation's care and adding one more layer of attention to the same star. The papers cite each other across decades. Bond's 2013 paper cites Chamberlain and Aller from 1951. Bulgen and Vale's 2024 paper cites Bond. Some future paper, 20 years from now, will cite Bulgen and Vale and adjust the number again. And so HD 14283 sits at its coordinates, 191 light-years away, moving at hundreds of kilometers per second through the halo of the Milky Way, on a trajectory that has carried it through this region of the galaxy for longer than there has been an Earth, longer than there has been a Sun. The light leaving it tonight will not reach a telescope until well after the year 2200. The people who will receive that light have not been born. The instruments that will receive it have not been built. The cosmological model they will compare its age to has perhaps not yet been written. Now let us pull back one more time. The James Webb Space Telescope and HD 14IO283 are, of course, only two threads in a much larger fabric of ongoing measurement. The age of the universe is not measured once. It is measured continuously by dozens of independent methods, each refining the others, each carrying its own systematic uncertainties, each tended by its own quiet community of researchers who have spent careers on a single piece of the puzzle. Consider the globular clusters, spherical concentrations of hundreds of thousands of stars distributed in a halo around the Milky Way, gravitationally bound, formed early. The two most carefully studied are M92 and NGC 6397, both visible from northern latitudes through modest telescopes. Their main sequence turnoff, the point where the brighter stars begin to leave the main sequence and head toward the red giant branch, is one of the most powerful age indicators in stellar astrophysics. Brian Chaboyer at Dartmouth College has spent more than 3 decades refining this technique, calibrating its systematic uncertainties against improved opacity tables, improved nuclear cross-sections, improved measurements of helium abundance. The current estimate for the age of M92, from a 2017 paper by O'Malley and collaborators in the Astrophysical Journal, is approximately 13.2 billion years, with an uncertainty of about 300 million. NGC 6397, from work led by Luca Pasquini at the European Southern Observatory, returns a similar number. These are not single-star measurements. They are population-wide constraints, averaged over thousands of stars. They are, in their own way, an independent check on the age of the oldest objects in our galaxy. And they come back, repeatedly, somewhere between 12.5 and 13.5 billion years, comfortably less than the age of the cosmos, older than nearly anything else we can measure. Consider also the white dwarf cooling sequence. When stars like our Sun exhaust their nuclear fuel, they shed their outer layers and leave behind a hot, dense remnant the size of Earth, but containing roughly half the mass of the Sun. These remnants, white dwarfs, cool slowly through pure radiation on timescales of billions of years. Find the coldest white dwarfs in a globular cluster, measure their luminosity, and you get an independent age estimate. Harvey Richer at the University of British Columbia and Brad Hansen at UCLA pioneered this technique through the 1990s and 2000s, using the Hubble Space Telescope to image clusters deep enough to catch the faintest white dwarfs. For NGC 6397, their analysis returned an age of approximately 11.5 to 12 billion years. Again, consistent. Again, comfortably within the age of the cosmos. There is something quietly beautiful about how many ways we have to measure the same thing. Now let us add one more thread. The age of the universe is also constrained, indirectly, by Big Bang nuclear synthesis. In the first few minutes after the initial expansion, the universe was hot enough to fuse hydrogen and helium and trace amounts of lithium. The observed ratios of these light elements today, in primitive galaxies and in old stars like HD 140283, depend on the baryon density and the timing of those early minutes. The lithium abundance in HD 14283 itself, measured by François and Monique Spite in 1982 at the Observatoire de Paris, became one of the cornerstones of this constraint. The so-called Spite plateau, the nearly constant lithium abundance found in metal-poor halo stars, set an independent expectation for what the early universe had produced. HD 140283 sits on the Spite plateau, almost exactly where it should. There is also a technique, less famous than the supernova ladder, called cosmic chronometers, developed by Raúl Jiménez at the University of Pennsylvania in the early 2000s, refined by Andrea Cimati and Michele Moresco at the University of Bologna. It uses passively evolving early-type galaxies as cosmic clocks. By measuring the differential age of these galaxies at different redshifts, one can infer the Hubble parameter directly, without needing a distance ladder at all. Moresco and his collaborators have, since 2012, published a series of papers in the Journal of Cosmology and Astroparticle Physics refining the technique. Their current measurements are consistent, within uncertainties, with both the early and late universe Hubble values. They lean slightly toward the early universe number. Each of these methods is its own decades-long project. Each has its own working group, its own conferences, its own careful arguments. And they all, in different ways, return numbers that converge on something close to 13.5 to 14 billion years for the oldest things in the universe, and just under 14 billion for the universe itself. The convergence is what makes the tension interesting. If the methods returned wildly different numbers, the field would have many problems to solve. They do not. They return numbers that agree mostly within a few 100 million years. And within that small window of disagreement, HD 283 keeps appearing. Right at the edge. Always at the edge. Now let us return to the star itself, because the question of HD 283 does not end with one paper. Even after Bulgin and Vale's careful 2024 analysis, the work continues. The Gaia mission, operated by the European Space Agency since 2013, has been measuring stellar parallaxes to unprecedented precision. The third data release, Gaia DR3, was published on June 13, 2022, and gave a parallax for HD 1.0283 with an uncertainty of about 10 microarc seconds. That distance measurement is now better than anything Bond had available in 2013. The fourth data release, Gaia DR4, is planned for late 2026. The fifth, Gaia DR5, is currently scheduled for 2030 and will incorporate the full 10 years of Gaia mission data. With each release, the distance to HD 283 will be refined, and with each refinement, the inferred age will shift slightly in one direction or another. Other measurements continue too. The TESS mission, which provided the photometry for Lundqvist's asteroseismic analysis, is still observing. Its extended mission has been approved through 2025. The Plato mission, also a European Space Agency project, is scheduled for launch in 2026 from Kourou. Plato will provide asteroseismic photometry of unprecedented quality for tens of thousands of stars, including almost certainly HD 283. The age estimate from that data, when it arrives in the late 2020s or early 2030s, will be the most precise yet obtained. What we know in 2026 is that HD 283 is somewhere between 12 and 14 billion years old. What we do not yet know is exactly where in that range it falls. And there are other ancient stars now, beyond HD and 283 itself. Anna Friebel at the Massachusetts Institute of Technology, working with Norbert Chrislieb at the University of Heidelberg, identified a star called HE 15-30901 in the southern constellation Libra. Their 2007 paper in the astrophysical journal Letters used radioactive thorium and uranium abundances to date the star directly. Each atom of thorium-232 has a half-life of 14 billion years, almost exactly the age of the universe. By comparing the ratio of thorium and uranium to stable rare earth elements, Friebel and her team derived an age of 13.2 billion years, with an uncertainty of about 2 billion. The number is consistent with everything else. The technique is independent. There are now more than a dozen stars known with confirmed ages exceeding 12 billion years. HD 283 is the closest and the most carefully measured. It is not unique. It is one of a small population of survivors from the first 500 million years of the cosmos, scattered through the halo of our galaxy, each carrying its own light from a moment in cosmic history that is otherwise inaccessible to direct observation. Consider what this means for a moment. The stars that are still here from the cosmic dawn are, almost without exception, low in mass. They are not the giants that dominate younger populations. The giants from that era are long since dead. What we see now when we point a telescope at the halo is the surviving low-mass relics, the slow-burning ones, the ones too small to die quickly. HD 223 is one of these, approximately 80% of the mass of the Sun, burning hydrogen so slowly that, even after 12 or 13 billion years, it has only just begun to leave the main sequence and head toward the subgiant branch. If you wanted a witness to the cosmic dawn, this is the kind of star you would build. Small, patient, almost without metals, capable of running, almost unchanged for the entire age of the universe. There is something about this number that I have not been able to set aside since I first encountered it years ago. The star was not designed to last this long. Nothing was. The fact that it sits in our galactic neighbourhood at all, that we can point a telescope at it and read its surface temperature to within a few tens of degrees, is an accident of the particular history of this corner of the universe. Now let us widen our gaze one more time. The question of HD 4.283 sits inside a larger question that cosmologists have been wrestling with for at least a decade. The question of whether the universe is, in fact, as old as we currently say it is. The Hubble tension, which I described earlier, is one piece of this. It is not the only piece. There is also the question of the early universe expansion rate, of the contents of dark energy, of whether the simplest model of cosmology, the lambda CDM model, is still adequate to the data. Lambda CDM has been the working framework since the late 1990s, since the discovery of the accelerating expansion by Adam Riess, Brian Schmidt, and Saul Perlmutter, work that won the Nobel Prize in Physics in 2011. It has been remarkably successful. It has fit, with adjustments, almost every observation made since then, but it is showing strain. The Hubble tension is one strain. The JWST early universe galaxy problem is another. A third, called the sigma 8 tension, concerns the clumpiness of matter in the late universe and disagrees, at the 2 to 3 sigma level, between early universe and late universe measurements. Each tension on its own could be explained by an undetected systematic error. Together, they have led a growing number of cosmologists to wonder whether the framework itself needs an adjustment. Catherine Heymans at the University of Edinburgh and Hendrik Hildebrandt at the Ruhr University Bochum have been leading the weak gravitational lensing surveys that surface the sigma 8 tension. Adam Riess has continued to refine the S80ES collaboration's distance ladder. Wendy Friedman at Carnegie has published competing measurements that suggest the Hubble tension may be less severe than the high values imply. The community is not unanimous. It is working. If the framework does need adjustment, the age of the universe could shift, modestly, perhaps by a few 100 million years in either direction, not by billions. The basic timeline, from the initial expansion through nucleosynthesis, through recombination, through structure formation, is well constrained by independent lines of evidence. But the exact number on the age, the 13.797, could move, and if it moves, HD 140283 moves with it. Its age relative to the age of the cosmos depends on which numbers the next decade settles on. There is a quiet humility in this. We do not know exactly how old anything is. We know to within a fraction of a percent. We know better than any prior generation. But we are still, in this year of 2026, calibrating our oldest yardsticks against each other, and the calibration is not yet complete. There is something I have noticed, watching this field over the years. The people who do this work do not, in private, sound like the certainty you encounter in the popularizations. They sound careful. They sound like they have lost prior numbers before and expect to lose this one. They understand that the universe is patient with their inquiries. The universe is not, in any sense, in a hurry to be understood. Now let us think for a moment about what the next decade may bring. The Vera C. Rubin Observatory, located on Cerro Pachon in Chile, achieved first light in 2024. Its legacy survey of space and time will image the entire southern sky every few nights for 10 years, beginning in earnest in 2025. It will discover, by current estimates, hundreds of new type Ia supernovae each night, refining the late universe distance ladder. The extremely large telescope, also in Chile, on Cerro Armazones, is under construction by the European Southern Observatory. Its primary mirror, when complete in 2028 or 2029, will be 39 meters across, larger than any existing optical telescope by a factor of 3 out today. It will be able to measure the spectra of individual ancient stars in the halos of other galaxies, extending the kind of analysis we have done on HD 140283 to objects 10 million times more distant. The Euclid mission, launched from Cape Canaveral on July 1st of 2023, is currently mapping a third of the sky to measure the distribution of galaxies and the geometry of cosmic expansion. Its first major data release is expected in 2026. The Simons Observatory in the Atacama Desert in Chile will measure the cosmic microwave background with a precision that surpasses Planck. The Lightbird satellite, planned for launch by the Japan Aerospace Exploration Agency in 2032, will look for the imprint of primordial gravitational waves on that background. Each of these instruments will, in some way, sharpen the constraint on the age of the universe. Each of them will, in some way, change what we say about HD 283. There is something I would like you to hold for a moment, fellow night watcher. The star is not waiting for us to figure this out. It is moving slowly through the halo of the Milky Way. Its surface is oscillating at frequencies of about 200 microhertz, in patterns that encode its mean density and its core structure. Its photons are leaving in every direction at the speed of light. Some of them are still on their way to telescopes that have not been built. Some of them passed our planet 190 years ago, when the first photographs were being taken in Paris, and now belong to whatever is downstream of us in their trajectory. The star is doing what stars do. The universe is doing what universes do. What changes is our ability to read what they are doing. Now let us widen the gaze one final time before we begin to close. The age of HD 140283 is a small thread in a very large tapestry. The tension between this star and the universe it lives in has been, for more than a decade, one of the quieter scandals of modern cosmology. Not a scandal of crisis, a scandal of patience. A small number sitting at the edge of a much larger number, refusing to be tidy. The work continues. It will continue past the lifetime of every astronomer currently working on it. Howard Bond is now in his late 70s. He is still listed on the faculty at Pennsylvania State University, still occasionally publishing, still part of the slow conversation. Gail Bulgen, whose 2024 paper appears to have finally resolved the headline tension, is in the middle of his career at the Université de Liège in Belgium. Anna Friebel at MIT continues to find ancient stars in the halo. Brian Chaboyer at Dartmouth continues to refine the globular cluster ages. The conferences continue. The papers continue. The light continues to arrive. That is the strange thing about long-running questions in astrophysics. They are not solved by a single clever mind. They are solved by the slow accumulation of better instruments, better measurements, and patient revision of small errors. The story is not the discovery. The story is the patience. Consider how many people across more than a century have looked at this single point of light. Walter Adams at Mount Wilson in 1912, examining its spectrum and noting something peculiar in the strength of its iron lines. Joseph Chamberlain and Lawrence Aller in 1951, formally identifying it as a metal-deficient subdwarf and recognizing what that meant about its age. Beatrice Tinsley in the 1970s, who first articulated rigorously the idea that the chemical composition of stars carried the fingerprint of cosmic time. The Spites in Paris in 1982, measuring its lithium. Howard Bond and his team at the Space Telescope Science Institute. In 2000 and again in 2013, refining the parallax and the bolometric luminosity. Mikkel Lundqvist and his collaborators, with TESS photometry in 2025. Bulgen and Valle, with tailored abundances the same year. Each of them did their piece. Each of them, in some sense, handed the question to the next person. The star did not move. The work moved. Now let us return. We began this story under a moonless sky with a telescope pointed at the constellation Libra, at a faint star sitting at the very limit of unaided vision. The star was approximately 190 light years from where we stood. It is still there. It is still doing what it has been doing for somewhere between 12 and 14 billion years. It is burning hydrogen, slowly, in a core that has only begun, in the last fraction of its lifetime, to feel the strain of exhaustion. It is moving through the halo of the Milky Way at about 300 kilometers per second, on an orbit that takes it far above the plane of the galactic disk and then back down again, on cycles of tens of millions of years. I think about Howard Bond sometimes. Not the public Bond, the one who gave talks at conferences and answered questions for journalists when the 2013 paper made headlines. The private Bond, the one who sat at a desk at the Space Telescope Science Institute in Baltimore in the early 2010s, working through the parallax data, working through the bolometric corrections, working through the metallicity errors. The one who, by his own account in interviews afterwards, did not entirely believe his own number when it first came out. 14.46 billion years, plus or minus 800 million. The age of his own star, by his own best methods, exceeding the published age of the universe by something close to 700 million years. That moment must have been a very quiet moment, not a moment of triumph. A moment of, let me check this again. The astronomer's life is, in some sense, the life of returning to the same number and asking whether it can possibly be correct. The good astronomers never stop doing this. The very good ones are willing to publish numbers they do not entirely believe, with uncertainties that admit the possibility of being wrong, and then to live, professionally, with the slow process of finding out. They are willing to be wrong in public. They are willing to spend a career revising a single line in a textbook by 1/10 of a billion years. They are, in their own way, citizens of a country whose currency is precision. What still stops me about this story is not the headline. It is not the apparent paradox of a star older than the universe. It is what came after the paradox. The corrections, the careful revisions, the diffusion models, the asteroseismology, the Gaia parallaxes, the 100 quiet adjustments made by scientists who were not trying to be famous, that brought the number into agreement with the universe, give or take a few 100 million years. The system worked, not because anyone shouted, because everyone went back to the data. There is something about that, in a moment when so much of public life is loud, that I find quietly stabilizing. The universe does not respond to argumentation, it responds to better measurement. HD 428283 has not changed in any meaningful way in 12 billion years. Our number for it has changed several times in a decade. The star is unbothered. The star is patient. The star is older than our questions and indifferent to our answers. Now let us follow the light one more time. The photons from HD 428283 that arrive at our eyes tonight left the star approximately 190 years ago. 1836. Charles Darwin had just returned from the voyage of the Beagle. The first daguerreotype photograph was 3 years away. There were no electric lights anywhere on Earth. The photons left the surface of a star that was already, at that moment, older than every story humans had ever told. They crossed the vacuum at 300,000 kilometers per second, in absolute silence, bending only slightly through the gravitational fields they passed. They arrived continuously, at the same rate they left. Some of them struck the photographic plates Walter Adams loaded into the spectrograph at Mount Wilson in 1912. Some struck the detectors Chamberlain and Allaire used at Yerkes in 1951. Some struck the photomultipliers used by François and Monique Spite at the Observatoire de Haute-Provence in 1982. Some struck the fine guidance sensors of the Hubble Space Telescope during Bond's parallax campaign in the late 2000s. Some are striking the detectors of TESS in low Earth orbit. Some are striking our retinas, or the mirrors of telescopes pointed at the star tonight, right now as you listen. The star did not change. The instruments changed, the reading changed, the conversation continued. That is the story. Now let us think about who comes next. The Vera C. Rubin Observatory is operational, completing its first survey runs. The extremely large telescope is rising on Cerro Armazones. Plato will launch later this year from Kourou. Gaia DR4 will be released later this year. Gaia DR5 in 2030, with the full 10-year baseline. Each of these will, in some small way, refine our number for HD 428283. Some young astronomer somewhere is right now finishing a doctoral thesis on a piece of this puzzle. Their name's not yet known to me. It is not yet known to them in the form their reputation will eventually take. They are simply doing the work, going back to the data, asking whether the number can possibly be correct. And the star is waiting for them. The star will outlast them too. By the careful estimates of stellar evolution, HD 428283 has another 2 or 3 billion years before it exhausts its core in earnest and begins its slow journey toward the white dwarf stage. There is no human timescale on which the star is in any hurry. There is in fact no timescale on which we matter to it at all. We are looking at it. It is not looking at us. And yet there is, I think, something like a relationship in that asymmetric act of attention. We point our telescopes. We measure carefully. We argue about the small details. The light which left long before we existed lets us see what the star was doing when. And in the seeing, we are briefly in contact with a piece of the universe that does not need our explanation in order to keep being what it is. We are the ones who notice. That is perhaps our small contribution to the equation. We notice. We measure. We write it down. We pass it forward. There is a phrase that has stayed with me since I first encountered it years ago from the astronomer Carl Sagan. He said that we are a way for the cosmos to know itself. I have always thought that was a generous formulation. The cosmos, after all, was doing fine before we showed up. But there is a sense in which it is true. A star like HD Phantom 0283 is, in itself, only a star. It does not know that it is 12 billion years old. It does not know that there are other stars. It does not know that, on a small water-covered planet, about 190 light-years away, there are creatures who have spent the last 100 years trying to figure out exactly when it was born. The light is still travelling. The detectors are still recording. The papers are still being submitted to the Astrophysical Journal and the monthly notices of the Royal Astronomical Society. The conferences are still being held in Heidelberg and Pasadena and Tokyo. The arguments are still being refined. Methuselah, our oldest known neighbour, still sitting in Libra, exactly where Howard Bond measured it, doing exactly what it has done since long before the sun and the earth and the rocks under our feet existed at all. Older than the iron in our blood. Older than the carbon in our breath. Older than nearly every heavy atom in the room you're sitting in tonight, with the possible exception of the hydrogen. And we sit here briefly, in this small fold of the cosmos, asking what it means that the star is so old. The honest answer is, we do not entirely know. We know what we have measured. We know what we have ruled out. We know that the simplest story, of a star older than its universe, did not hold up to scrutiny. We know that the more complicated story, of careful corrections converging on something close to the age of the cosmos itself, is currently our best account. The numbers will move again in the years to come. The methods will improve. The conversation, fellow night watcher, is not finished. That is what astronomy is. That is what stars do. They wait patiently for us to look at them carefully enough. If this story stayed with you, a like helps other patient listeners find this archive. There is more waiting for you in the playlist. Other objects, other distances, other questions that have outlived their askers. The light is still travelling. The telescope is still open. The conversation continues. Thank you for staying with me through this story.